from the beginning, we want to do the sorting with special requirements. Yeah. Here, 1, 2, 3 special requirements. All right, these three special requirements. All right. In order to design the special sorting algorithm, we need to consider a special data structure. The data structure, we want to use array to construct it. But if we just use array directly, we cannot store a binary tree in it. So we have to modify. We have to add some extra property to this array so that we can store a binary tree in it. Why binary tree? Yeah, some of you may ask me why we like to store a binary tree in an array. The reason is this condition number 3. Look at our requirements, 3 requirements. The third one, maintain dynamic data efficiently. We want this property. So what do you mean maintain dynamic data efficiently? When a new data item comes in, we need to insert it into the array, and we want to have big theta, this one. We want to have big theta of log n insertion. That's the binary search type insertion. Binary search type insertion. All right. So for that reason, in order to have the binary search type of property for this array, we need to build a binary tree in this array. Otherwise, how can you do the binary search, right? Yeah. Without a binary tree, how can you do a binary search, right? Yeah. So that's the, all the story behind our last time 15 minutes introduction. So now, today, we continue the story and we get the details, how to make this structure happen. Yeah, how to get this advanced data structure to support this special sorting algorithm. All right. Next, our goal, we want to build the binary tree structure in an array. Yeah. Some of you may ask, what do you mean? A binary tree structure in an array, right? Array is an array. How can you connect to a binary tree? Yeah. So to answer that question, we only need one key property here. So that is represent the parent-child relationship. For the nodes. Yeah. In order to make a binary tree in order to make an array to represent a binary tree, we need to address that parent-child relationship among certain nodes. Yeah, that's the key property. Yeah, if we can do that, then the binary tree structure is there. All right. Yeah. So that's the main thing we need to do. Yeah. The question, how to modify the array? All right. Yeah. Array. What kind of information do we have in an array? When we represent locations of the array elements, we use indices, right? Array indices. Yeah. So the main information we have, array indices for locations of array elements. That information we can use to describe a binary tree. Yeah. All right, so let's look at our data part. Remember, we want to support dynamic data operations. Yeah. All right, so when we work on a sequence of data, at the beginning, we can sort the data in the array, right? Yeah. At the beginning, before we try to make the operations more efficient, let us sort the array first. Yeah. So that's the initial sorting. Yeah. All right. With that initial sorting, so we can assume this array, the data at a certain point, it is ordered. Yeah. But after that, when new data comes in, the order information or the order property is violated, right? The order property could be violated by the new data, right? So we need to fix it. If there is some order violation, we need to fix it. Yeah. So here the question is, if you want to fix the order, to recover the order, how much cost you need to pay? Yeah, so that is the main question. We don't want to pay too much cost. We want to reduce that cost. Okay, yeah. So to make it in order, yeah, we want some efficient way to do it. Yeah. Here we can consider that insertion operation, right? Yeah. Because you insert a new data item into an ordered array. We did that before in our insertion sort. We did that, right? Yeah. But in the insertion sort, we pay this much. We pay this much cost, big theta of n. Big theta of n. Yeah. The reason we pay this much, remember, there is a shift operation. Yeah. Because after we find a location for the new element, we need to make a space for it. We shift the elements to the right to move the elements, some of the elements to the right to provide a location for the new element. That is the reason we have to pay this big theta of n, the total cost. All right. Yeah. But here, we're not very satisfied with big theta of n. Yeah. Because we do not feel it's good enough. We like to have faster operation here. Yeah. So we don't want to take the insertion, the shifting type insertion. All right. Yeah. Our target, we want to have this big theta of log n. Yeah. This is much better than big theta of n. Yeah, much better than that. Yeah. Big theta of log n. Yeah. So here the question is how to get it. Log n. Yeah. Log n that connects to the binary tree structure. Yeah. All right, so here. So let's look at how can we modify insertion operation. Insertion operation, remember when we do insertion, we have two ways to do it, right? Yeah. We did a few examples. We can have two ways to do it. The first way, linear search, that's in our insertion sort. But second one, based on binary search. When we need to find the location for a new element, we just do binary search. Because the data is ordered, so we can do binary search. Data is ordered, all right? Yeah, binary search. All right. So here, to get a big theta of log n, let us try the binary search way. Okay. All right. Question, how to get it? How to get a binary tree corresponding to binary search operation. All right. So we need to let us do some preparation here. Yeah. First, we need to introduce a new data structure. Second, with array as its underlying data holder, yeah, because we know array is very simple. If we really build a new data structure from scratch, that could be very expensive. If we can just use the array to store the data and do some extra work, and after that we can represent a binary tree, that would be good. Yeah. All right. Maintain the parent-child relationship. Yeah. How do you represent a binary tree? Yeah. So this is the main property you need to specify in a binary tree. Yeah. Start from the root. You need to have a location for an element that corresponds to the root of the binary tree. After that, two child nodes of the root, right? Left child node, right child node. Yeah. Then after that, you have another level parent-child relationship. That structure you have to represent in your new data structure. Okay. So we need to fix that details. Yeah. 8.2, binary tree structure in array. All right. So let us work on the details. How to build a binary tree inside an array. Here we introduce the heap data structure. So we call this new data structure the heap. Yeah. But what's the definition of a heap? Yeah. Let us describe its main property. After that, so we understand the meaning of this heap data structure. Yeah. Properties we need for this data structure: use an array as the underlying storage object. Yeah. So that's the, simple fact. Yeah. Next one, it should be a near complete binary tree. But near complete, we know the meaning of complete binary tree, right? But here, we cannot require complete binary tree. Why? Because in order to have a complete binary tree, the total number of elements should satisfy 2 to the k minus 1, this condition. But in general, we do not have this condition. Power of 2 minus 1. So our next best thing is we allow the bottom level not necessary full, so we call it a near complete. Yeah. Here, let me draw a figure. Yeah, this one. Look at this one. Yeah. This is a binary tree, right? And we call it a near binary tree. Why? Yeah. Look at the bottom level. Okay. Yeah. Above this dotted line, all the levels above the bottom level are full, right? All the level except the bottom level are full. Only the bottom level may not be full, right? So if a binary tree has this structure, we call it near complete binary tree. It's not complete. Yeah. If it is complete, the bottom level should also be full. Yeah. But here, in order to draw this binary tree for all n, yeah, not just n, for all n, then we can only take this near complete requirement, binary tree requirement. Yeah. All right. So that's the definition of this term. Yeah. Number 3, sufficient space for dynamic data. Sufficient space. So this requirement is not easy to satisfy because we don't know how much space is sufficient, right? We don't know how much dynamic data we need to store. Yeah. So that answer may not be easy. Yeah. So we need to find a way. Without knowing how much dynamic data we may have, we need to find a solution. Okay, yeah. So we need sufficient space. Yeah. But we cannot predict exactly how much space we allocate to this data structure. All right, yeah, yeah. So here, let us talk about this question a little more later. Yeah. So we have a solution, yeah, for it. Yeah. We can modify our data structure again and again to store more data. If we detect our current array is not large enough for new data, we need to replace it with a larger array, right? Yeah. Because we know array, the size of the array must be fixed. You cannot change it. After you declare an array, you cannot change its size. Its size must be fixed. So the only way to store more data, we replace a smaller array by a larger array. That's the way we can store more data if the current array is not large enough. Yeah. So we will talk about that problem later. Number 4, certain relationship among nodes. That's the parent-child relationship. The question, how do you represent parent-child relationship in an array? Yeah. That's the most important question for this heap data structure. All right. Now, this question, how much space is sufficient? Yeah. Nobody can predict, right? If nobody can predict, but we need to find a solution. Yeah. All right. So our method, yeah. So let's look at how do we change array sizes when we have more and more dynamic data. Change array sizes. All right, yeah. This change, actually, we change arrays, array objects. We change array objects. One array is an object, right? We treat one array as an object. So we change array objects. Yeah. So here, let me describe the procedure, the typical procedure, right? Yeah. At the beginning, we do not know how much data we will have in the future. Yeah. But at the beginning, we need to declare some array to store data, right? Yeah. So we do in this way. We assign certain amount of space to an array initially. At the beginning, you just estimate, okay, certain number of locations for the array elements. Yeah. Enough to cover existing elements. Or usually people assign more than necessary locations to store current elements. Yeah, because you need to give some room for growing, right? So usually when you assign memory locations to an array, you assign more locations than the number of array elements. All right. Yeah. You just estimate. Yeah. All right. After that, then to store dynamic data, we need to keep adding data. So the number of locations occupied by the data items are growing. Eventually, we reach the size limit, right? Eventually, we reach the limit of the size. It's full, array is full. So that full array cannot be used to store more data items anymore. When that happens, you have to declare a new array with larger size, then copy data from the smaller old array to the new larger array with more locations. Then you can add more data items, right? Yeah. Do data copy. Yeah. In that way, you can keep growing. You can keep adding new data items. Yeah. That step is costly, pretty expensive, right? But you have to do it. In order to store new data items, you have to do in that way, although it's pretty expensive, right? Yeah. All right. So when a threshold, yeah, that size limit is reached, yeah, here the threshold, yeah, the threshold usually is smaller. Yeah, here I use this threshold term, smaller than that limit of size. So the reason is simple. We set some threshold smaller than the size limit. So before we reach the limit of the array size, we detect the array is near full, close to full quickly. So we need to do preparation, right? When it reaches the threshold, we need to start do preparation. If it reaches the size limit, then you have no room to do preparation, right? You have to stop. You have to, create a new array, do data copy. At that time, then the whole algorithm the whole program has to stop, right? So we don't want that happen, right? So we want to stop preparation early. So we set some threshold smaller than the limit size. Then we at least we have some time buffer. We have some time allow us to do some preparation work. Yeah. So a new array with larger size is created and copy the data to the new array. That takes some time, right? Think about if the array is large, is very big, when you do data copy, it takes some time, right? Yeah. All right. So usually it is expensive to copy a large array. Okay. Yeah. Look like this graph, right? Before you do copy, so the response time is quite small. Yeah. But then this place, when you do data copy, suddenly your CPU time is used for that big data copy. Yeah. Then suddenly the response time gets slower. Okay. After it completes, then the response time becomes faster. Right. That kind of performance bottleneck is not good for real world applications, right? Some customers, if they're not lucky, so they need to wait relatively long time when the data copy happens. Think about that. So that's not a good solution. That's not a good solution. Yeah. A better solution is like this. We want to avoid this bottleneck model. Yeah. What do we want to have is like this graph. Yeah. That means we try to spread the workload of that data copy evenly in a larger period of time. Yeah. So that is when we detect, here, when we detect the threshold, the threshold is hit, then we start a preparation. Okay. And we create a new array, do data copy immediately, right? Yeah. Little by little, we spread the workload. How about that? Yeah. When you insert, let's think about this way. All right. When you insert a new data item, you copy 10 old data items. How about that? Every time you insert one new data item, you copy 10 old data items. How about that? 1 to 10 ratio. Okay. Next time you insert another new data item, you copy 10 old data items. Something like that. So in that one, because when you copy 10 old data, it won't be very slow, right? Only 10 old data copies. It won't be very slow. Okay. But in that way, you spread a data copy, the workload, in a relatively long period of time. But you can make your response time acceptable, okay? Not too slow. Slightly slower than non-copy situation, but completely acceptable by your customers. Yeah. Think about that model. Okay? Yeah. So in the real world, so you like to have the second solution. Okay. All right. Yeah. So here, after I spend this much time to explain, this data copy issue, then from now on, later, after that, we should not worry about, the data size part, right? Yeah. How do we enlarge the array size? Yeah. This is the way we enlarge the array size. Okay. Yeah, this way. Yeah. Here I just write the idea, but if you need to write the code, yeah, you need to do a lot of work to write a code, implement this idea. But it's doable. Yeah. If you have this idea, it's doable. Yeah. Actually, in Java has many data structure using this idea. Yeah. So inside Java, yeah, in the old way, there is a vector data structure, right? Vector data structure, it can change its size, in this way. When you grow the vector size, then every time it double its previous size. So that's the internal algorithm to, increase the data storage locations for vector data structure. Yeah. All right. Yeah. So let's move to the next topic. 8.3, heap property. The main parent-child relationship. That's the heap property. So let's look at that definition. Yeah. Relationship among heap nodes. Yeah. A binary tree is stored in an array. Yeah. It's possible if we can define the relationship among heap nodes, then we can represent a binary tree. Yeah. Someone check your microphone. Yeah. Microphone. Yeah. Let me look at. All right. Make sure. Yeah. Right. All right. Yeah. Make sure. Pavan, your microphone. Yeah. Oh, all right. Okay. All right. Yeah. Let's continue. Yeah. All right. All right. Yeah. Relationship, parent-child relationship. Yeah. All right. By imagination. Why I say by imagination? Because you cannot see a concrete binary tree in an array, right? You can only imagine a binary tree in an array. Okay, yeah. All right. Let's consider a node in the array. And also, we will convert this node as one in a binary tree. Yeah. Its location, how to describe its location? By its index. If we know the index of an element, we know its location. Yeah. So our control, we will apply our control on the array indexes. Yeah. Now, through array indexes, we can define the relationship between two nodes, parent-child, especially parent-child relationship. Yeah. All right. We only need to define the relationship between two indices. That means two locations in the array. Yeah. All right, so now that's the definition part. Yeah, look at this diagram. P refers to the parent node. P:(I), that means the index, array index for the parent node is I. Then its left child, L:(2I). We will use 2I location, that element corresponds to the left child of the P node. Similarly, R, right child, we will use the location 2I plus 1 that location for the right child of the P node. How about that? Simple. Pretty natural, right? I points to two possible locations. 2i location, 2i plus 1 location. Now, how about that idea? If it works or not. Think about that. It works or not. Okay, in this way. Yeah. Here, yeah, I cannot be 0. If we define the relationship in this way, we do not allow index I to be 0. The reason is simple. If I equals 0, then think about if I equal to 0, then 2i equals I, right? Its left child, 2i, has the same location as its parent node. That's not allowed. Because we at least we need a 2i not equal to I, right? So that means in the array, the 0 location cannot be used for any node in the binary tree. So A of 0 is never used. Or we can say in this way, A of 0 cannot be used to store any binary tree node. You can use it to store other information, but you cannot use it to store binary tree node, any tree node. All right, yep. So that's, after that, then we can represent the parent-child relationship. Okay, yeah. So, with this definition, this structure, yeah, parent-child, this kind of structure, yeah, there are two types of heaps. Yeah. Max heap and min heaps. Yeah. Maximum, minimum. Yeah. Yeah. Max heap property, yeah, the value stored in the parent node, A of I, should be greater or equal to A of 2i and A of 2i plus 1. Yeah. So that is the parent value should be greater or equal to 2 values in its child nodes, 2 child nodes. That's the max heap requirement. Yeah. But for the min heap, then we just change the inequality direction. Yeah. Less than or equal to. Yeah. Parent node value smaller or equal to any of its child value. Yeah. But these two different types of heaps, the only difference is that inequality direction. Other than that, everything the same. That means we only need to study one of them. Then the other one, we just modify the other one slightly. We can quickly get solution for the second heap type. Yeah. So in this class, we just study max heaps. Yeah, the min heaps, just simple modification. Yeah. So we don't worry about the other one. Yeah. So let us consider max heaps from now on. Yeah. All right. Next, a max heap example. Yeah, let me just give you a simple max heap example. Yeah. All right. Okay, yeah. Yeah. Look at this one. You, at every location, you need to check max heap, the heap property, max heap property. Yeah. Look at these 3 nodes. No problem. Max heap property. Yeah. This part, max heap property, no problem. Yeah. Look at this part. Max heap property, no problem, right? Yeah. Then also the last triangle. All right. Yeah. Max heap property, no problem. Yeah. So let me draw a little smaller. Yeah. This last triangle. Okay. Yeah. So no violation of that max heap property, then we can say this is a max heap. Look at that. Okay. Yeah. So it's pretty easy to construct a max heap. Okay. All right. Here, the underlying array. Yeah. Can you imagine we can store that binary tree, near complete binary tree, to an array here? Yeah, because the zero location cannot be used to store any node. Yeah. So we leave it empty and we start from position 1. Position 1, we put 16 there. Position 2 and 3, 2 child nodes, 14 and 10. Yeah. Next one, 2 child nodes of node 14, 8 and 7. So next 2 location number 4 and 5. Next 2, number 6, number 7, 2 child nodes for element at location number 3, location 3, and so on. Okay. Yeah. At the end, you can see we store that whole binary tree in an array. And other than the first 0 location, all the remaining locations are occupied, right? Yeah. So that's pretty good. Only that 1 0 location is not used. All the remaining locations are used. The waste is very little. Yeah. So that's acceptable for us. Yeah. So at least we complete that binary tree storage inside an array. That task we completed. All right. Yeah. Okay. Next, maintain the heap property. Maintain. When a new element comes in, you may break the structure of the max heap, right? You need to recover it. So that kind of work you need to do. That's the maintenance work you need to do. All right. When the heap property is violated due to some properties, insertion, deletion, etc., how to fix it? Yeah. Let's consider a typical situation. How to fix? Now here, there could be a violation among these 3 nodes, P, L, and R. The question, if you detect there is a violation among these 3 nodes, then you need to swap some elements to recover the max heap property. Yeah. How to do it? That's pretty simple. Yeah. Here, yeah, we can imagine this. Violation occurs locally. Yeah. Every time we examine 3 nodes, 3 local nodes like this, yeah, and check if there is a violation. When we detect a violation, so then we apply some operation. Yeah. All right. Yeah. But the question is, yeah, here. All right. And here, when we detect a violation, let us just consider, this place, it's a max heap. Yeah. This place is a max heap. Yeah. And also, this place also max heap. Yeah. Only at a P location, the max property is violated. Let's assume that situation. Yeah. How to fix it? Local fixing operation. Now we want to do the local fixing operation. All right. Yeah. But if we complete local fixing operation, you need to make sure globally no violation, right? Yeah. You need to check everywhere there is no violation. Okay. Yeah. All right. So here we define that local heapify operation. Local heapify. Yeah. So what's that? Yeah. So we use the recursion approach. Yeah. Yeah. Here I just, use some pseudocode to represent that local heapify operation. Yeah. So this is the general case. Yeah. Now, yeah, because here we consider the max heap property. Yeah. If A of I less than A of 2I, that's a violation, right? Regarding the max heapify property, this inequality is a violation. So we need to fix it. Yeah. All right. If this condition happens, then we store that 2I location in that largest variable. This largest is a variable name. We temporarily store that 2I location in this largest variable. Temporary storage. All right. Yeah. Later we may change this. Yeah. So here, the first time we store the 2I value to largest variable. Else, that means A of I greater or equal to 2I, right? If A of I greater or equal to 2I, then we store I to that largest variable. Yeah. Okay. Yeah. But we need to check for the right child, right? We just check the left child. Check the right child condition. If A of largest less than A of 2 plus 1, that's a violation, right? Yeah, that is the violation. Yeah. Then this time we should store 2I plus 1 to this largest variable. You can see after these 3 assignments, yeah, we may have 3 different assignments to largest variable, right? 2I, 2I plus 1. Right? After these 3 assignments, we make sure the largest variable stores the index of the largest among the 3 elements, right? PLR, 3 elements, the largest value. We store that location into the largest, all right? Then, at the end, we check if we need to do any swap operation. Yeah. If largest not equal to I, yeah, that means we need to swap, okay? Then we swap A of largest and A of I, that operation. After that, we fix the max heap violation, max heap property violation locally. Yeah, that's local in this particular location. Yeah. After that, we need to check other places. This is just the one place. Yeah. Local heapify operation. Yeah. All right. Now, but we don't worry. Yeah. For the global, so we can, use a for loop to go through all the locations. Yeah. All right. Then 8.4, heap example. Yeah. So this time, so let us look at some concrete heap example. Yeah. All right. Max heap example. Here in our goal, we want to get a max heapify. Yeah, here it's a max heapify example. All right. Here you can see there is a violation. Yeah. After we examine all the locations in this heap, we detect the violation occurs at a node 4. All right. Then we need to apply heapify, max heapify operation. All right. Yeah. So based on our local heapify operation, we need to do swap between these two nodes, right? Yeah. A swap between these two nodes. The largest element among the three, 4, 14, and 7. 14 is the largest. So we swap between. After the swap operation, we move node 4 down to the left, but you can see it causes another violation. Here you can see another violation. So you need to fix it again. Yeah. You swap this time node 4 and node 8. That another swap. After that swap operation, you fix the max heap property violation. Yeah. After that, you examine everywhere. Yeah. All places, the max heap property is satisfied. Yeah. So that is a max heap. So you get a max heap. Yeah. Every time when you detect a violation, you can fix it in this way. So you will get a max heap after certain number of local heapify operations. Yeah. All right. Next example, building a heap. Now we consider another operation, how to build a heap. Now, given an array, given an arbitrary array, we won't have a heap, right? Given arbitrary, we won't have a heap. But we need to build a heap. After we build a heap, then we can use it to store dynamic data. Yeah, dynamic data. Yeah. So let us look at the details, how to build a heap. Yeah. Suppose this is a given array. Okay? Yeah. So definitely it's not a max heap. Yeah. Suppose our goal, we want to construct a max heap from this array. Okay. All right. What is the idea? We need to design some algorithm to recover, to rearrange the elements such that it becomes a max heap. Okay. Yeah. We just apply the max heapify operation. Max heapify operation, we just used before. Yeah. But when we apply it, we need to follow certain order, some special order. Yeah. Here, let me use this example to show you how to build it. All right. Yeah. When we start, we check the max heap property bottom up. Use the bottom up. Bottom up approach. Yeah. All right. When we start, first let's check from the bottom, rightmost bottom. Yeah. this order, rightmost order. So each level from right to left in that order. Yeah. Bottom up. Yeah. No violation, right? 16, node 16 and node 7, no violation. Then we go to the next one. Second local area. Second, 3-element local area like this. We detect there is a violation. So I put a star there, there is a violation. So we should apply local max heapify operation to fix it. Yeah. Swap between element 2 and element 14. Right? After that operation, we fix that local area. Then we move to the next local area here. 3-element local area. We detect another violation. All right. But this time to fix it, we need to swap element 3 and element 10. All right. After that swap operation, we move to the next 3-element local area, and we detect another violation. Okay. Yeah. Then we need to swap these 2 elements. All right. But after that swap operation, you can see when one here, there is another violation, right? Yeah. Look at that. All right. Oh, sorry. I did it wrong. All right. When we examine the local area, 3-element area, we should do swap operation between element 1 and element 16. 16 is larger than 14. Element 1 and element 16. All right. Yeah. After that, because when you move element 1 here, another violation, so you need to do another swap between element 7 and element 1. Then you fix that area. So you can see this local area, you need to follow the moving element all the way down to the bottom. Okay? Yep. Because that moving element may cause new violation. Think about that. That moving element could cause new violation. So you should check along the path. Everywhere when you move one element down to the bottom, you need to check violation, max heap property violation. Yeah. Until you know there is no violation. Okay, all right. So then the last local area, you need to check these 3-element local area, another violation. Yeah. So you need to swap these 2 elements. But when you swap, because element 4 is moving down, it may cause another violation. So you need to fix it by another swap, moving down, but it causes another violation, right? So you need to still apply another swap operation until it reaches the bottom or no violation is detected. Yeah. So these 2 things happen. Yeah. All right. So after the fix, now, yeah, just when you move down this element 4, it causes new violation here. So you need to fix this new derived violation. Yeah. All right. So after you move down here, another fix, you get this one. You get this picture. Okay. All right. Then after that, you can see this is a max heap. Now, you can see we did we did a local max heapify operation many times, right? Yes. You may feel it could be very expensive, right? Yeah. To do operations like this, it could be very expensive, right? Yes. Yeah, but how expensive it is? How expensive it is? We need to do some calculation. Yeah. And in our next part, yeah, because today we cannot do that. In our next part, we will do the computation. We will see the cost, this building cost, building a heap, that cost equals big theta of n. Big theta of n. Is that too much? Building a whole heap from the original array, is it reasonable? Yeah, that's a reasonable cost. Okay, yeah. So we accept that. Yeah. Build a heap, we accept that. Yeah. All right. Because this is not too bad, because this cost is initial cost. Initial cost, so that means we only pay this much cost once. Yeah. During the whole maintenance procedure, we only pay this cost once at the beginning. At the beginning, we build our first max heap, we pay this much cost. After that, when we maintain, every time when new data comes in, we only need to pay this much cost. Okay? After we pay this cost the first time, later we always, every time we pay big theta of log n, this much cost. Yeah. So that's not too bad. That's reasonable. Yeah. The first time we pay big theta of n, but after that we always pay big theta of log n. How about that? When a new data comes in. All right, yeah. All right, so that is this advanced data structure. So you can see it's not trivial, right? We need to do a lot of work. Okay, but not too complicated. Yeah, so if you follow closely, yeah, so you can handle this kind of data structure, right? There is no pointer. We define parent-child relationship without pointer, right? You do not need to maintain pointers. Okay, yeah. You just change, index. You just do swap operations. Okay, yeah, yeah. All right, yeah. Okay, yeah. So that's pretty much I like to cover today. Yeah.